Good morning, everybody. Thank you for the introduction. I'm very happy to be here. First time in Australia, first time living in the US since 2020. Very excited. So today I want to talk about the two recent papers that came out from my group, which was about fusion-based error correction and tailoring this method of error correction for bias noise. In this case, the bias noise is when fusion failures are biased, and I'll tell you what all of this means. So the work was done by my student Claudia, postdoc Jayhan, and in the second paper we collaborated with experimentalists on crowd pattern systems. Jun Lungin is an experimentalist in Jeff Thompson's group, who's the PI working with neutral patterns in Pittsburgh. Okay, so what am I going to talk about today? So I'm specifically going to focus on fusion-based error correction with something called as the XCTX surface code. What is fusion? Fusion is just measurement of two body operators, XX and ZZ. So if you have a system where you can't easily do gate operations, but your measurements are native to your architecture, then this is the way to go. So what I will consider the noise model is when fusion failures are biased. What I mean is that your hardware is such that your ZZ measurements are more reliable than XX measurements. This is a noise model that is relevant in linear optics and in dual resonant qubits in linear optical systems, as well as I will show you in metastable ytterbium atom qubits. So what I will show you is how to tailor fusion-based error correction such that when you have such biased fusion noise, then you are able to get high thresholds. The implications of our architecture in the linear optical system is that we are able to get scalable fault tolerance in the linear optical system with just 4 unentangled photons that are put in to realize a successful fusion. This was not possible earlier before our work came out. And in terms of the ytterbium atom qubits, you get a very high threshold and you can reduce overhead requirements. So I will go through this in my talk. My aim is to not try to finish all the slides. I would be happy if you ask me questions and have a discussion. We have whiteboards, I guess I can use them if needed. Okay, so here's the outline of my talk. So I will talk about the XCTX surface code, the XCTX cluster state, then go to fusion-based error correction, then talk about the application in dual rail qubits as well as ytterbium atoms. So let's start with the XCTX surface code. So the XCTX surface code was invented here. It involves qubits arranged in the planar lattice. And in this diagram, the qubits are on the vertices, and the stabilizers are the 4-body XCTX operators around each locale. And you have here I've drawn the poly X operator and the poly Z operator for this logical qubit, and you have the distance to X errors and distance to Z errors, which are the height and the length of your rectangle. So when we think about doing error correction with the surface code, we usually think about the circuit model, in which what we do is for every stabilizer, we have an ancilla qubit. We prepare the ancilla qubit in the plus state, and we do a bunch of control knot and control phase gates between the data qubits and the ancilla qubits, and then we read out the ancilla qubit. And we do this many times, and we compare the measurement outcomes from one round to the next round and determine if there was errors or not. So if both the rounds have the same measurement outcome, if I just get ancilla measured in the ancilla measurement outcome is 0, 0, and 1, 1, then that means no error happened. But if we, in between the two rounds, the ancilla measurement changed, it went from 0 to 1 or 1 to 0, then you know something went wrong. And this is what your error syndromes are. And you collect this information and you decode the noise. The nice property about the XCTX surface code is that it has 2D symmetries to Z errors. So if you have Z errors in your system, then the syndromes that are generated lie on a 2D plane. What this means in terms of decoding, if you're familiar with minimum weight perfect matching decoding, it just means that you have to now match, you have to find perfect matchings of a graph that is 2D rather than 3D, and so this reduces this makes decoding easier and you get higher thresholds. In terms of if you don't know what minimum weight perfect matching is, then you can think about this 2D decoding graph as the decoding graph that is generated when you have a quantum repetition code. And a repetition code has really high thresholds, and therefore, if you have high bias, you have more Z errors than X and Y errors, then you get a high threshold with the XCJ. Moreover, what's nice is that if you can change the distance to X and Z errors depending on what your bias is. So if you have only Z errors in your system, for example, you can just choose dx equal to 1, and you basically just have a repetition code, a linear code, and you can basically reduce overhead requirements in this case. Okay. Now, let's see how we might do the same error correction procedure in a measurement-based picture. So I'm drawing this plaquette over here again. So at time t equal to 1, you had your ancilla, you did your control phase and control NOT gates, and you measured the ancilla, so you know what your syndrome, you know the measurement outcome. Now, before you repeat this measurement again, now what I would want to do is teleport each of these data qubits into fresh qubits. So for each of the data qubits, I will add 2 more qubits. So for this qubit over here, I will add 2 qubits. For this qubit here, I have 2 more qubits. For this qubit here, I have 2 more qubits, and so on. And the convention that I'm following is shown over here. So if I draw a circle, open circle, then that means that the qubit is prepared in the 0 state. If I draw a dot, that means the qubit is prepared in the plus state. Now what I will do is I will do C0 gates between the qubits as shown here. So if I have an edge between a dot and an open circle, that means it's a C0 gate with control on the dot and the NOT operation or the target on the open circle. Now I will measure each of these qubits. By doing so, I will basically teleport this qubit to this qubit, this qubit to this qubit, this qubit to this qubit, and then this qubit to this. So I'm just teleporting information. This is just like your Nielsen and Chang teleportation circuit that I'm actually implementing. And the measurement that I will, convention I will follow is that the qubits that are prepared in the 0 state will be measured in the Z bases, and the qubits that are prepared in the plus state will be measured in the X bases. I will call these qubits as Z-type qubits and X-type qubits. So Z-type qubits are prepared in the 0 state, measured in the Z bases. X-type qubits are prepared in the plus state and measured in the X bases. Okay, so now once I measure these qubits, I have teleported my information onto these fresh qubits over here. And now I can actually add another ancilla and measure the stabilizers again. So basically what I'm doing is I'm going to teleport, measure stabilizers, teleport, measure stabilizers, and so on, and I can just keep on doing this. So this is you can think about this as teleportation-based error correction or measurement-based error correction. They're equivalent. Now the state that you get before making those final measurements that I showed you is basically you could have instead of doing teleport measure, you could have created at once with all these C0 gates a big 3D state and then done all the measurements at once. And so the state that you get after doing the gates is basically your cluster state. So now, how does error correction actually proceed here? Remember, this qubit was measuring the stabilizer of the code at time t1. This qubit was measuring the stabilizer at time t2. Now remember, if I was doing circuit-based error correction, I would just compare. I would just add these two measurement results. But here, because I'm doing teleportation in between, I've actually picked up some polycorrections which are based on the measurement outcome of these center qubits. So now I can't simply compare this measurement with this measurement. I have to compare these two measurements while accounting for these center 4 measurements as well. So in fact, in this case, we can see that the error correction, to determine syndromes, you have to add the measurements from these center X-type qubits and the Z-type qubits at the top and the bottom. And so that becomes your syndrome. And this is just happening because by teleporting, I've picked up some poly corrections in the middle. All right. So this kind of cluster state that we have created using C0 gate is what we call a bias-preserving cluster state, in the sense that as I teleport, I don't convert physical Z or X errors to other forms of errors. So physical Z errors remain physical Z errors throughout this teleportation circuit. If I had used a conventional method of teleportation in cluster states, which is based on using control Z gates, then I would have converted a Z error on one qubit to an X error on another qubit, and so on. And so by using C0 gates, I'm able to make a bias-preserving cluster state. It keeps the nature of noise consistent. It preserves the nature of noise. Whereas if I've used a conventional cluster state, I could not have done that. And you can see more discussion about these bias-preserving ways to create the cluster state in our paper over here. Now, the important point, though, is that, oops, how do I go back? Yeah, so the important point is that by using this bias-preserving teleportation technique, I'm actually able to properly implement the XZX surface code. I'm able to preserve the symmetries of the XZX surface code in the corresponding XZX cluster state, which means that if I have Z errors anywhere in my system, I will get, again, a 2D decoding graph, which is what happens in the regular XZX surface code. And so even in this XZX cluster state, I'll get high thresholds to bias noise. If, in fact, I had used control Z gates to do teleportation instead of control NOT gates, this would not happen. If I try to teleport XZX surface code using the control Z gate, it actually reduces to the regular CSS surface code because your errors just get converted from one layer to the next. Okay, so in summary, I've shown you the XZX cluster state. It is defined on a decorated graph rather than the simple graph of regular cluster states like the RNG cluster state. So here I have two types of qubits, Z-type qubits and X-type qubits. Z-type qubits are prepared in the 0 state, X-type qubits are prepared in the plus state. The gates are control NOT gates, with the control of the X-type qubits target on the Z-type qubits. These gates are all commuting with each other, so you could prepare this cluster state at once. You can apply all the gates at once. The teleportation and error correction, it proceeds by measuring the X-type qubits in the X bases and Z-type qubits in the Z bases. For error correction, you can look at each unit cell of this crystal structure that we have. So for error correction, you will combine the X measurement results of the X-type qubits on the faces and the Z measurement results of the Z-type qubits on the top and the bottom face of the unit cell. You have to add all of that together. If there's no errors, this cell stabilizer should be 1. Should be 0. If there's an error, it should add up to 1. Now, when I talk to my experimentalist friends, they don't like the cluster state because they think you need like a big 3D structure, but that's not the case. You just basically need 2 layers, 2 planar layers of like the surface code, and you just basically teleport information back and forth between those 2 layers, and in time create this 3D lattice-like structure. Okay. Again, I want to emphasize the point about noise in the cluster state. If you have Z errors, then the syndromes are restricted to 2D planes. So if, for example, there's a Z error on this qubit over here, it will trigger the syndromes in the unit cell in the back and in the front. If you have a Z error on this qubit, it will trigger these syndromes to the left and the right unit cell, and so these Z syndromes form a 2D, disconnected 2D planes. And only when you have X errors on the Z-type qubits do you get syndromes out of the plane. And so if you have X, Y, and Z errors, you get a 3D graph. If you have only Z errors, you get a 2D graph. Okay. So now what is the implication also beyond the threshold? What is the implication of having biased noise? What is the implication of having 2D decoding graph? So if you have highly biased noise, so if you have only Z errors, then you actually just need one layer of this cluster state. And that one layer is basically a cluster state version of the repetition code. So if you have only Z errors, this is the only cluster state you need to correct for your Z errors. And again, this looks like you need like a big 2D lattice, but in fact, you just need two linear chains of qubits, like shown over here. So you just have these two chains, and you do your gates and entangle the qubits, and now you just measure the qubits in the first chain, and you have teleported the information to the second chain, and then you do your gates again, and then you measure the second chain, and now you've teleported information back to the first chain. So you just need these two chains and teleport information back and forth, so you're now creating like a repetition code itself. Okay, so in our paper, we did some numerical simulations to really see in the circuit level setting what is the threshold improvement I can get with this XZX cluster state. We assume that we have biased noise, so Z errors are more likely than the X and Y errors. I can define a bias, which is the ratio of the Z errors to X and Y errors. So if I have only Z errors, no X and Y errors, then eta is infinity. If for the depolarizing noise case, eta is half. So on this figure over here, I plot the threshold versus the bias for the XZX cluster state, and as you can see, I get an improvement almost by a factor of 2 of the threshold as the bias increases. If I had used the conventional RAG cluster state, which is basically a teleported version of the regular CSS surface code, then I do see a slight improvement in the threshold with the bias, but not very much. It turns out that the RAG cluster state is slightly more robust to X bias noise, and we also compared that. And again, we see with these green dots, there's slight improvement in the threshold with bias, but not as much as the improvement with the XZX or with the XZX cluster state. Any questions so far? Okay, so yeah.
Is there an asymmetry
But for X noise, yeah, and the way to think about it is in the RAG cluster state, you measure all qubits in the X spaces. So naively, you would think that it should be X errors don't really affect your X measurement outcome. So that's one way to think about how you get a slightly better threshold to X errors. Okay. Now let's go to thinking about fusion-based error correction. So now I want to implement this cluster state using fusions rather than gates. So the idea is that in some hardware, it might be difficult for you to do gates, but it's the native operations that are available to you are fusions or two-body measurement operations. So what you do is you somehow probabilistically generate smaller cluster states, like a few body cluster states, 4-body, 6-body, 8-body, just a few body cluster states, and then you stitch them together using these two-body measurements to get a larger cluster state. So that's just fusion-based error correction. If you're familiar with what PsiQuantum does, then PsiQuantum follows the fusion-based architecture. So what is our contribution in this area? We design the resource states and the fusion network. We optimize the resource states and fusion network such that when I have biased fusion failures, that is when my Z errors are more reliable than X errors, then I get high thresholds. And the whole idea is that I want to make sure I design my resource states and fusion network such that when the XX information is wrong, then that induces errors only on the X-type qubits. That introduces Z-type errors on X-type qubits in my cluster state, because I know if I have Z errors on my X qubits, I will get a 2D graph, everything reduces to a repetition code, and I'll get high threshold. So that's the fundamental idea behind our construction. Concentrate your dominant errors to Z-type errors on X-type qubits. That's it. And I will show you that this helps us improve the requirements for fault tolerance in linear optics and for this metastable determinant qubit. Okay, so let's see how I can use fusions to stitch smaller resource states. So there are many ways to think about it. In fact, even in our paper and also this paper from Sci Quantum, which was the first time I think they called it, they gave this technique a specific name, which is fusion-based error correction. So that there are two ways in which we can use fusions to build a whole cluster state. I'm just talking about one of those techniques, which is based on half fusions, which is that one measurement, one type of measurement, XX or ZZ, makes a cluster state, and the other measurement actually, the other part of the fusion actually does the measurement of the cluster state itself. It's a little bit confusing. I will explain it to you. So suppose I'm trying to join two smaller states, and I have a Z-type qubit here, which has two X-type neighbors, and again a Z-type qubit here with two X-type neighbors. And I just do XX measurements on these two Z-type qubits. Now I'm measuring 1 degree of information on 2 qubits. That means I'm left, after the measurement, I'm left with 1 free qubit, 1 effective qubit. So basically what has happened is that after doing this measurement, I can think about these 2 qubits as 1 effective Z-type qubit, where the Z of this effective qubit is actually Z tensor Z, and X of this effective qubit is X tensor I. So I just do this one measurement to create one effective qubit. And so what I've done is I have joined these 2 separate graphs into one graph, modulo polycorrections on the neighboring X-type qubits, which depends on the XX measurement outcome. So if the measurement outcome is 0, there's no polycorrection. If the measurement outcome is 1, then I apply Z's to these 2 neighboring qubits. Now suppose I want to fuse 2 X-type qubits. So I have X qubits with neighboring X and Z, another X with the neighboring Z and X, and I now measure ZZ on these 2 X-type qubits. Then I will merge these 2 qubits into one effective X-type qubit with effective Z operator Z tensor I and effective X operator X tensor. So again, I've merged 2 different cluster states into a bigger single cluster state where the qubits on which I perform the measurements actually just becomes one effective qubit. So now with this, you can I will tell you what are the resource states I'll be looking at. So I look at this 6-body resource state. It's drawn in a weird way, but it's just like a ring. It's just qubits arranged on a ring with neighboring control Z and control 1 gates. Now for every unit cell in the cluster state, at the corners of every unit cell, I'll place 2 copies of this of the 6-body resource state. So you see that I already have half the bonds of the cluster state with me. These other lighter gray lines are the bonds that are missing that I want to create. So I'll now start stacking these. When I do this for every unit cell, there'll be a unit cell at the bottom, and I will stack the 6-body resource states as such, and I'm now going to fuse these 2 qubits into one single qubit, and you'll see that these 2 missing bonds from the first unit cell will be inherited from this second unit cell here. This is just a diagrammatic intuition. And I just keep on doing this for every unit cell. So basically, I merge the neighboring X-type qubits and the neighboring Z-type qubits for each pair of unit cell. And I will get the effective cluster state lattice. So now these 2 Z-type qubits merge to this single Z-type qubit, these 2 X-type qubits merge to this X-type qubit, and so on. And so now you can see the actual XZX cluster state lattice emerging from this. Now, once I have the cluster state, what do I want to do? I want to measure the Z-type qubits in the Z bases and the X-type qubits in the X bases, right? So that means that I have to measure Z tensor Z of this qubit and X tensor X of this qubit. So that's the effective Z and the effective X. But remember, combining the first XX measurement and the second ZZ measurement is actually the fusion measurement that we're talking about. these two measurements, XX and ZZ, commute. I could have actually performed ZZ before XX, doesn't matter. The reason I told you to perform XX first is to give you an intuition for why this approach actually builds the right cluster state, that's all. And similarly, the ZZ measurement on this qubit and the XX measurement on this qubit combine to give you a fusion. So just by doing a single fusion measurement, now you can see why I get the cluster state and why am I able to get, why am I able to do error correction. Okay. Now let's look at what happens to when I have biased fusion errors. Remember, that's the whole point, that my errors are biased such that my XX measurements are more likely to be faulty than the ZZ measurements. Okay, so if I look at this again, note that based on this XX measurement, I have to apply the Z poly corrections to these neighboring qubits. So if my XX measurement is incorrect, that means that I don't know whether I should apply identity or a Z to those qubits. That means an incorrect X measurement is actually introducing a Z error on these two X-type qubits. That's exactly what I wanted. I wanted to concentrate fusion errors onto errors on the X-type qubits. Similarly, in this second type of fusion, an incorrect XX measurement just means that I'm measuring the incorrect XX measurement is like a Z error on the X-type qubit, because a Z error would cause an incorrect measurement of X operator. So again, I see that in both the cases, if there is faulty XX fusion measurement, it only introduces an effective Z error on the X-type qubits. In particular, in the two cases I will be looking at today, the XX measurements are not just incorrect, they are erased. That means my experiment puts its hands up and says, hey, I did not do the XX measurement correctly, do not trust me. So that's an erasure error. That gives you more information that tells you the location of the error as well. So in that case, specifically, we see that it's equivalent to applying a Z error on these two qubits with 50% probability and a Z error on this qubit, on this qubit with 50% probability. It's a Z error on a known location. That's important because my experiment has told me something has gone wrong here. Okay. So now with this, I will move on to how I can use this construction to get higher thresholds for in photonics and as well as the atomic qubits. But are there any questions at this point? No questions. I'm doing a good job. Okay. So what are linear optical dual rail qubits? It's basically the qubit is defined by which mode a photon is in. So if you have two modes, if the photon is in mode A, you call it qubit 0, and if the photon is in mode B, you call it qubit 1. The nice thing about the dual rail qubits is that these single qubit gate operations are essentially free in linear optics. You just need beam splitters, photon number detectors, and phase shifters, and you can do a universal single qubit gate operations. The problem, however, is that multi-qubit gates are not easy to do with linear optical systems. You can do measurements, you can do multi-qubit measurements, you can do destructive multi-qubit measurements, but you cannot do gate operations easily. And so that's one problem, and of course we have to deal with photon loss. So you can have a situation where there's no photon in either of the two rails. This is also like an erasure error because you need to, when you make a measurement, you need to detect one photon at least one of the two rails. If you don't see any photon, you know something went wrong, and so this is also like an erasure error. Okay. Why is this not moving? So let's see how you do fusions in linear optics. So remember, fusions is like measuring XX and ZZ. So I need to basically distinguish between these four bell states. So I need to distinguish between 0, 1 plus 1, 0, 0, 1 minus 1, 0, and 0, 0 plus or minus 1, 1. I need to distinguish these four states. So now I put the two dual rail qubits through two beam splitters with four photon detectors. So if I input 0, 1 plus 1, 0 state, then you can show that you should see detector 1 and 3 click or detector 2 and 4 click. If you had put 0, 1, minus 1, 0 state, then you would see detectors 1 and 4 clicks or the middle two detectors click. So you can completely discriminate 0, 1 plus 1, 0 and 0, 1 minus 1, 0. But unfortunately, with this setup, you cannot discriminate 0, 0 plus or minus 1, 1. What you can discriminate is 0, 0 and 1, 1. So if you had put in 0, 0 state, you would actually get two detections in the first detector or the second detector. If you had put 1, 1, you would get two detections in the third or the fourth detector. So this means that half the time you're able to discriminate the state, the other half of the times you cannot discriminate the state. This means that you succeed half the time. You are completely able to get both XX and ZZ information. The other half of the time you don't get the XX information, but you still know Z's. You still know the qubit were both zeros or both ones. That means you still can get Z1 comma Z2 and then multiply them to get Z1 times Z2, but you have no information about X. So in this case, we say that the fusion has failed 50% of the time, but the times it has failed, you have only lost X information. And you know that you have failed. You know you have lost the X information because you saw from the detector output. So this is again like an erasure of XX information. Of course, you can have photon loss as well in this network, and in that case, all information XX and ZZ is going to be destroyed. So inherent fusion failures only destroys XX information. Photon loss destroys all information. Okay. Now, 50% with 50% success rate, you basically can't do anything. So you have to boost the success probability of fusions. You do that by adding extra photons, adding auxiliary photons into your fusion network. So you add, so in this paper, they showed that you can add entangled photon states into your network of beam splitters and photon detectors. And in that case, you can suppress the fusion failure probability to 1 by 2 to the n by using 2 to the n minus 2 entangled photons. In this paper, they actually showed that for a special case, when you want n equal to 2, that means you want a success probability of 75% or failure probability of 25%. For that specific case, you can actually use 4 unentangled photons at the input. It's very hard to generate entangled photons. So if somehow you were able to tolerate 25% failure rate, then you can actually use the scheme proposed in this paper and use only 4 unentangled photons to successfully have a fusion with 25% error rate. That is actually what we achieved with our fusion architecture. Okay, so now before showing you the numerical results, let me recap the error model that we are going to simulate to get these numerical results. We are going to consider that I'm using n extra photons in my fusion network to get a failure probability of 2 to the minus n. Of course, there's going to be photon loss at a rate p loss per photon. So every photon can be lost with probability p loss. So now the overall probability that a fusion actually succeeds depends on the inherent success rate, so that's 1 minus p fail, times the probability that no photon was actually lost. And using this relation, the formula for the probability that no photon was actually lost is here. The lower p fail I want, more photons I have to add to my network, and higher the probability that one of these photons are going to be lost. So if I actually try to decrease p fail and increase this first part, I will actually end up decreasing, I'll take a hit and start decreasing the second part. So there is a balance between how many photons you add before which you actually start making things worse, because more photons are now going to be lost. So now I'm going to show you the numerical results. What we do in our simulations is we fix p fail. So in particular, we say, okay, as if I had used 2 extra photons in my fusion network, my failure probability will be 25%, otherwise it'll be like 12.5% and so on and so forth. So this is 1 by 2 to the 3 is the failure rate when I use 3 extra entangled photons. 1 by 2 to the 4 is when I use 4 extra entangled photons and so on. And now I fix p-fail and calculate the amount of photon loss I can actually tolerate. And this is the curve I get. Please focus on the blue lines, not the red lines. I did not talk about the red lines. I talked about the blue lines. They perform better anyways. So the solid blue line is using our construction, our 6-ring state. And the dotted line is using the previous best 6-ring construction, which is from this cyclone paper. We clearly outperform, in terms of threshold, we clearly outperform the previous construction in a very important region, actually. What is an important region? First, if you just notice the x-axis accounts for when I have no photon loss, so I only have to protect against fusion failures. In this case, I get a threshold of about 35% with our fusion construction, whereas you get slightly less than 25%. This is actually about 24% with the previous best results. What does this mean? It means that we have a chance, with our fusion network, we have a chance to actually just use 2 auxiliary entangled photons or 4 unentangled photons to reach scalability. You could not do that with the previous best approach. So as expected, we are able, in this specific region, we are actually able to do error correct against fusion failures as well as photon loss and achieve scalability, again by using 2 entangled photons or 4 unentangled photons, whereas with the previous best strategy, you need at least 3 entangled photons to reach, to be scalable. I'm going to pause here for a second to see if there are any questions. How much time do I have? 15 minutes, okay. Yes.
So I was just wondering what the rules of the game here are in that, like in the Psi quantum paper, they also consider 2 like encoded resource states, so states with more qubits, and so here you're comparing just the
basic, yeah.
The basic
so, yeah,
string.
basic. We're not using encoded states, but you could actually use those encoded states and combine that with our strategy and even make it better.
I suppose that was sort of the question.
Yeah. So I think the claim is that, okay, the bigger initial resource states you make, you are going to improve the thresholds anyways. But just, we did not work, I think they used the Shore code as an initial resource state. We did not compare to that, just for simplicity. Anything else? Okay. Now let me talk about this other the other qubit system that I'm really excited about these days. It's the metastable ytterbium atom qubit. So in these atomic qubits, this is a Rydberg atom qubit. You encode the qubit in some metastable states of the atom. Not important what they are. I'm just going to label them as 0 and 1. That's where I encode the qubit. So when I have 2 of these atoms and they're sitting in the 0-1 states, the wave functions don't really overlap, and so they don't really interact with each other. So if I want to do 2 qubit gates, what I do is I have to excite the atom to the Rydberg state. When you go to the Rydberg states, they have larger wave functions, they overlap, and they start interacting, and that's how you do control Z gate between the 2 atoms. Now the dominant source of errors is actually coming from when you're in the Rydberg state, the atom can de-excite to the ground state or some other states into your system, which I've not really drawn, but there are many subspaces that your atom can go to, but that transition happens if you're in the Rydberg state, not if you're sitting in the qubit subspace. So what you can do is you can apply some extra laser pulses to see if there is any population in one of those other subspaces. And if you see any population in one of the other subspaces, say if you see a population in the ground state, then you know something went wrong. You know that your Rydberg state decayed and something has gone wrong to the qubit, and that's like an erasure error. So in this case, we expect that the probability of an erasure error is much more likely than the probability of a computational error or like a poly error. And I can define an erasure fraction, which is the ratio of the erasure errors to the total errors in your system. For pure erasure errors, that means I have no computational basis errors, R is 1. If I have only poly errors, no erasure errors, R is 0. So in this paper here, which was published in Nature last year, we studied this noise model in some detail and looked at the fact, we looked at how a surface code with this would perform, and we got high thresholds. But in a recent paper, we went more deeply into the noise model and discovered that, well, you see, most of you excite only the one state to the Rydberg state. So if you see that an atom has decayed to set the ground state, that means it must have come from the Rydberg state, and the Rydberg state did come from the one state. So in effect, seeing population in the ground state is equivalent to knowing that your atom had actually started in the one state. Or equivalently, it's like measuring the atom in the one basis, in the z basis. If you see an erasure, that means atom was 1. If you don't see an erasure, that means basically nothing happened. So we want to use this additional information, this information about biased erasures again now. Erasures happen only when I started from the one state, not when I started in the zero state. I want to use this information to further improve my error correction. So the first thing we did was go back and look at the circuit-based approach. So in this case, again, remember I'm doing measuring the syndromes by doing gate operations. Here I'm just, for simplicity, showing just 2 data qubits, and I'm doing a control phase gate between an epsilon and the data qubit, and a control NOT gate between the epsilon and the other data qubit. And the Rydberg atoms, I don't naturally have a control X gate, I have a control phase gate. So I implement a control X by sandwiching it with Hadamard's. And so after every gate, I actually apply a laser pulse to see if I had an erasure there or not. If I see an erasure, for example, here, I know the atom must have come from the one state, so I put a new fresh atom there in the one state and discontinue my gate operations from there. So in this case, we can look at the details in our paper. You can show that the error channel of the control Z gate is such that with probability P erasure, it gets a random error from this set, but only a Z error, identity ZI, IZ, or ZZ. And if there's no erasure, we just apply depolarizing noise model to both the data and the insula qubit. Now, what happens if I have a erasure in the phase gate that was involved in the C0 gate? In this case, the control Z, the channel of the control Z gate is still Z errors, but because of this Hadamard, the Z error is going to get converted to an X error. So because I don't have a kind of a bias preserving C0 gate here, the native C0 gate is going to convert Z errors to X errors. But nonetheless, we know that this conversion has occurred. We know that erasure happened there, so I know my Hadamard is going to convert Z to an X. And so I can show that actually for this C0 gate, the error is like this. It's randomly chosen from identity Xi, Ix, or Xx. And again, if I don't see any erasure, then I just apply depolarizing noise. So my noise is getting converted from Z errors to X errors, but I know exactly what type it is if it happened. I know it's either a Z type or an X type. At first, when Jeff Thompson brought this to me, I was like, it's not going to show any improvement because I know from my ZZX surface code, I need to preserve the symmetry. I need to have only Z errors or only X errors. So this is not going to show any improvement, but thankfully I was wrong. And so we did simulate the thresholds. The threshold versus the bias, and if you look at this orange dots, which is basically simulating this kind of circuit here, I see an improvement in the threshold up to almost about 10-ish% or so when I have really large biases. And now we also compared it to what if I had somehow magically a bias preserving C0 gate which did not convert Z errors to X errors. It does do slightly better than these orange dots, but only when the bias is really large. So in this case, we attribute the improvement that we are getting with this unbiased C0 gate from the fact that I'm kind of reducing my noise entropy. I'm making it easier for my decoder by giving it more information about whether there was an X error or a Z error. In fact, we can we simulated the same noise model, but for the regular CSS surface code, and we exactly got the orange dots back. Which means that this improvement is not coming from the fact that we're using an XZX surface code, it's coming from the fact that we're using, we have more information about noise in the system. But the a little bit annoying thing is that because I'm converting Z errors to X errors, now I can't use a repetition code because I have equal number of Z errors and X errors. So I have to use a square XZX surface code or a square CSS surface code. I cannot just use a simple repetition codes because I have to make the distance to X errors and distance to Z errors to be equal. So this was a little bit annoying. If I had bias preserving C0 gates, then I could have actually used a repetition code because my X errors would still be suppressed and repetition code would be fine. So to overcome this challenge, we looked at, can we actually do something better with fusions? Can I have a fusion-based architecture which has high thresholds, but which also doesn't convert Z errors to X errors, so that I can reduce my hardware requirement by just using a rectangular XZX surface code or like a repetition code or something? Fortunately, the answer to that question is yes. So in this fusion-based approach, I use a slightly different resource state. I use this 8-ring resource state, which can be prepared using, just a regular, like a very simple control phase gate space circuit. I put some hammer gates here, and after this circuit, I check whether there was any erasure. If I see any erasure anywhere, I discard this resource state and try again. So this is like a post-selected resource state. Only when I'm sure there's no erasure in my resource state, only then do I put that resource state into my fusion network. So basically, the only errors coming from the resource state is actually the poly errors, because those are the ones that don't get detected. But erasures are basically now completely removed. Okay, so the next thing I do is I want to have a fusion circuit. I want to have a fusion circuit which also has biased erasures. That means I'm going to try to measure XX and ZZ. But I want to make sure that when erasures happen in my atom, it only destroys XX information, it doesn't destroy ZZ information. Again, I'm using the same intuition from the photonic systems. So this is a circuit that we came up with. So I'm trying to measure Xi, Xj, and Zi, Zj between these two qubits. I prepare an ancilla qubit in the plus state, do my control phase gates. And after every control phase gate, I check whether there was an erasure or not. If there was no erasures, then I measure all of these qubits in the X spaces. The measurement outcome of the ancilla effectively measures the ZZ between qubit I and qubit J. And by measuring the qubit I and qubit J in the X spaces, I get Xi comma Xj, and I can multiply them to get Xi times Xj. So this, in the absence of erasure, this circuit does the right thing. It measures Xi Xj and Z Xj. Now what happens if there is an erasure? If there's an erasure in the ancilla qubit after my first control Z gate, then I just stop. I don't stop everything, and just go and measure my data qubits I and J in the Z basis. And I just multiply them to get the Zi, Zj measurement outcomes. I will not ever get Xi Xj. I can never recover Xi Xj once I see an erasure in the ancilla, but I can still recover Zi, Zj by this. Now, if I have an erasure in qubit J, an erasure in qubit J, if I see it there, again, I don't do the next control phase gate. Once the qubit is erased, once the qubit J is erased, I already know that it was measured in the 1 basis. So I already know that MZ is 1. And I just measured Z on the first qubit. And I just then multiply this measurement outcome with 1, and that's my Zi, Zj information. And similarly, if I I just basically continue doing this. If I see an erasure in qubit I, I just discard everything and I just say measure this atom. This was already measured in one state, and I'll just measure this qubit J. So in this kind of adaptive approach, I can, if I see an erasure, I can always recover the Zi Zj measurement outcome. I will never recover XXJ, but that's okay. I'm only destroying one type of measurement. So this is a bias preserving fusion circuit which does not use any CNOT gates at all. It uses only control field. So this is the overall protocol. I'm just going to run over this very quickly. So we basically first start by preparing a single layer of the cluster state. We have we arrange post-selected 8-ring states in a lattice like shown over here, and I just do XX measurements on the neighboring Z-type qubits. So I get this effective layer, single layer of the XAZX cluster state. Now I stack several layers like this on top of each other in a staggered manner, and then do control phase gates between nearest neighbor X-type qubits. And so this gives me the entire XAZX cluster state. And remember now, at the end of the day, I have to measure the Z-type qubits in the Z bases. To measure the Z-type qubit, if secretly means I'm measuring Zi tensor Zj on each of those qubits. So again, combining this XX measurement with the final ZZ measurement is like I'm actually doing a fusion on those Z-type qubits to begin with. So basically this step 2 of measuring XX and this final step 5b is making a fusion measurement. I could have everything in between commute, so I could have done these measurements together before doing any other step. So in fact, I can write down like a shorter version of this 5-step protocol. The first step is arrange the post-selected resource states in layers, which are, and these layers are kind of arranged in a staggered manner. Then we fuse the neighboring Z-type qubits, and at the same time, we can actually do the control Z-gate between the X-type qubits. These operations are happening on different qubits, so I could actually apply them all at the same time. And then finally, I just measure the X-type qubits in the X bases, and I'm done. And in this, again, we can show that if an XX measurement outcome is erased, that means that I will apply a incorrect Z polycorrections to the X-type qubits. So again, errors in fusions are only introducing Z errors in my X-type qubits. So everything is bias preserving. I don't get high. The other important thing is that here you can actually change the size of the cluster state depending on your X and Z errors in your system. So you should think about this cluster state like this. This direction is like the DZ, distance to Z errors. This interlayer, this layer is, the number of layers you stack is dx. It's how much X correction you want. And this horizontal direction is like the time direction, how many times you want to teleport your XAZX cluster state. So you can actually, if you don't have any X errors, if you only have Z errors in your system, if you only have erasure errors, you actually just need one of these layers. And again, one layer of the XAZX cluster state is, if you remember, just a repetition code, which I could implement with just 2 single lines, 2 chains of Q. So this is a hardware efficient protocol. In fact, in the fusion picture, this repetition code in time, so this is a 3 qubit repetition code in time. Time is going in the horizontal direction, can be just implemented with 2 layers of your resource states in this fashion. Okay. The other nice thing about this compared to the circuit-based approach is that you don't need mid-circuit atom replacement. In the circuit-based approach, if you saw an atom was missing, you have to bring a fresh atom there before you do anything else. Here, it doesn't matter. You were nowhere in my protocol did I tell you if you see an erasure, put a fresh atom in. That was not required. Okay, so again, numerical simulations. We plot threshold versus the error fraction, the erasure fraction, and we get super high threshold. This star marks the point when RE is equal to 98%. So in these ytterbium atom qubits, we expect in practice your RE is going to be about 98%. And so for that R, we get a threshold of about 10%. Here, our thresholds are also always higher than what we achieved with the circuit-based approach. Not much higher, but still high. Okay, so I'm gonna leave with this slide. So we introduced a new kind of fusion-based architecture, which provides high threshold against biased fusion failures. All this work is like really related to my need to understand what makes a good qubit and what makes a good code. So clearly, what we have shown is that what makes a good qubit is not just thinking about if it has high fidelity or low fidelity, or the fidelity as a single number is not the right thing to look at. What is important to look at is a noise entropy. How much different errors are what are the different kinds of errors that can happen in the system? This idea of looking at noise entropy was introduced to me by Steve Fleming, and I don't know what happened there. And of course, what makes a good code is you need to find codes that have additional symmetries to the noise happening in your system, which was the idea introduced to me by Ben, who's right here. And he has a very nice paper on this. I had referenced to it earlier somewhere in the slides. I forgot to put it here. But yeah, so we should think about not the fidelity anymore. We should think about the noise entropy of physical qubits. And in terms of codes, we should think about what are the additional symmetries that I can use to reduce the overhead. I'll stop here.
Oh, great, thanks, Shruti. I think we have time for a couple of questions. So, well, start with Steve.
It's sort of quite an open question. So your XZX cluster state has sort of these preferred planes, and you've oriented it such that time goes along one of those planes. But is there ever a scenario where it would make sense to orient time to go across the different planes?
It's weird. Like I chose to do it that way, but you can draw time axis anywhere. It's like it's up to you. But like, if I think about time in this preferred direction, I can make a connection to the repetition code, and I think about how I can reduce the overhead requirement. Like if I think about, it's totally valid for me to think about time actually going up like this. It's totally fine. I could choose to build my code that way. It just wouldn't like allow me to like reduce the overhead in some sense. I would not know how to do it.
What's the readout time for the measurement?
Readout for the erasure detection?
Yeah, relative to the other gate times.
So it's actually slow. But the nice thing about that is it can be slow because when you're doing the readout, you have finished doing your gates. So if erasure didn't happen, your atoms are back in your computational bases, and those atoms live for a very, very long time. So in that sense, the readout is fast compared to the lifetime of the atoms when they're in the computational state, but they might be long compared to the lifetime of the atom in the Rydberg state. Does that make sense? So you can't afford to take 2 times as long as a control Z gate to do that readout, because if there was no errors in the atoms, they're back in the computational bases and they can live there for seconds and several, I think hundreds of milliseconds or seconds or something.
Okay, why don't we take a question out of here?
So I have a question about the set and this X type of qubits. And you said you have this bias, so you can trust your X measurement is more. Is this true for both of these type of qubits, or only for the X type?
So the way I framed it, it was I can trust my Z measurements more than X measurements, but if somehow you have in your experiments the other way around, like if you can trust X measurements more than Z measurements, then you just want to concentrate your errors on the Z-type qubits. So Z-type qubits are if you have only X errors, then try to concentrate that on the Z-type qubits, and X errors on Z-type qubits will also give you a 2D decoding graph, but it will be perpendicular to the decoding graph of the other.
So thanks very much. That was awesome. So at the very end there, you mentioned actually doing a comparison of a cluster state-based approach or fusion-based approach and a gate approach, and you talked about the fact that noise actually came out better. So I was just wondering if you could give a flavor of like what's the reason for that the fusion-based approach actually has a higher noise tolerance.
So, okay, so so if I compare circuit-based approach to the fusion-based approach, the circuit-based approach is only able to exploit the fact that it knows more about the noise. So it's exploiting a lower noise entropy. The fusion-based approach is not only exploiting the lower noise entropy, but it's actually also exploiting the symmetry of the XCZX surface code itself to make decoding easier. So those are two things that are happening at once. If you have a bias-preserving C0 gate, then the circuit-based approach will be the same
Right.
as.
Right. Yeah. So okay. So that's based on there's not an accessible bias preserving
Yes.
gate.
Yes. Yes.
Another question? Ben?
Did you think about trying to find codes with other kinds of symmetries of this 2D one?
No, I want to hear more about that. Yeah. But but let's talk more. I have questions there.